welcome to the Miller household. AJ and Mitch here. We'll be discussing Newton's laws of motions on our Theoretical Thursday project. Newton's laws of motion are three physical laws that form the basis for classical mechanics. They describe the relationship between forces acting on a body and its motion due to those forces. Over nearly 3 centuries, they have been expressed in many different equations. The three laws of motion were first compiled and published by Sir Isaac Newton in 1687. Newton used them to explain and investigate the motion of many physical objects and systems.
Lawson here, and I'd like to discuss Sir Isaac Newton's first law of motion with you. The first law is an object in motion tends to stay in motion, and an object at rest tends to stay at rest unless acted upon by some outside force. More often than not, this force is friction, and what friction is a force that opposes motion or would-be motion between two parallel surfaces that are in contact. And what we don't see as humans is the molecular level of things. Many things appear and may seem like they're very smooth, but in reality, when you get down to the molecular level, what they look like is roughly this between the two surfaces. And when they come together, they compress, and maybe they move around a little bit, but they compress, and then when you move them, then they start grinding on each other. And in order to move, they have to start grinding. And what we don't see on this earth, because we just don't have it, and we haven't created anything like it, really is two totally smooth objects. They would be able to move in contact with each other freely, but we don't really see that. And so how this is important is just by walking. Or if I set this pen down here, I know it's not going to move because no force is acting on it. It literally will stay there for eternity, and it'll never be moved unless a force acts upon it. And same thing if I threw something in space where no force is acting upon it, it will never stop moving until it hits something, obviously.
Hi, I will be discussing Newton's second law of motion, which is if an object of mass is acted upon by a net force, it will experience an acceleration that is equal to the net force of the object divided by its mass. So this equation can also be manipulated to look like this. So the net force is equal to the acceleration times the mass. So we will be using this equation to look at a baseball that is being thrown at 90 miles an hour, and the baseball's mass is 0.15 kilograms, and the distance we are looking at is 2 meters, and we are looking for the sum of all forces. So first we are going to make this into meters per second. So 90 miles an hour is also equal to 1.5 miles a minute, which is also equal to 2,400 meters a second. So the speed in meters per second is 40 meters per second. So we're going to use this to find the acceleration, which is what we need in the equation. So the acceleration, to find the acceleration, we're going to set this equation up. So acceleration is equal to speed final squared minus speed initial squared divided by 2 change in x. So the final speed is 40 meters per second minus the initial speed, which is 0, divided by 2 times the change in x, which is 2 meters. So the acceleration of this is going to be 400 meters per second squared. So we're going to use the acceleration and the mass to find the net force that is acting upon the baseball. So net force is equal to acceleration times mass. We're going to plug in the acceleration, which is 400 meters per second squared, times the mass, which is 0.15 kilograms, and that is going to equal 60 newtons, or 10 pounds of force acting upon the baseball. It is also important to remember to sum up all of the forces, because in some situations you will have negative forces that go against the net force.
Cy Young here demonstrating Newton's second law. We're going to discuss Newton's third law of motion, which states that all forces exist in pairs. If one object exerts a force on a second object, then the second object simultaneously exerts a force back equal and opposite on the initiator. Therefore, the action and the reaction are simultaneous, and it does not matter what you call the action and reaction, but both forces are part of a single interaction, and neither force can exist without the other. And the best way to illustrate that is with another force equals mass times acceleration problem. So that's what we're going to do. So here we see force equals mass times acceleration. And we're going to do a problem with two boxes on a horizontal plane. And here's box number 1. That's 10 kilograms. And box number 2 is 5 kilograms. And if I were to push these boxes, regardless of the friction right now, if I were to push these boxes to the right with 20 newtons of force, I'm going to try, I know the force and I know the mass, now I want to find the acceleration, and also I'm going to try to find the force of contact between the boxes, but first I have to find the acceleration. So we have to find the net horizontal force first, and we see here that the force between these two boxes here, force 1 of box 1 and force 2 of box 2, equal 0 here because they're not moving. But the only force that's actually doing anything is me pushing the boxes to the right. So in order to find acceleration from this equation, we have to do A equals the sum of the forces over mass 1, the sum of the masses. Mass 1 plus mass 2. Now that's going to give us A equals 20 newtons over 10 kilograms plus 5 kilograms. And then that's going to give us 1.33 meters per second squared. So now we know how fast, if I were to push on these two boxes that are in contact to the right with 20 newtons of force, they would move to the right with 1.33 meters per second acceleration. Now, in order to find the force of contact between the boxes, we have to once again do another force equals mass times acceleration here. But this time the mass is only going to be the other box that's getting forced on, because this box is technically now has 20 newtons of force, and this box is just getting pushed. This box is doing the work through my hand that's pushing it. So it's going to be 5 kilograms times 1.33 meters per second squared. And that is going to give us 6.67 newtons of force between the two boxes, and that's 6.67 newtons of force with the contact there. In conclusion, these laws have stood up over 3 centuries and describe the very basis of everyday life.